All right, I'm going to go ahead and get started. I appreciate you coming at 11. I didn't have any emails about 10:30, so thank you. I would have felt really bad if someone was waiting at 10:30. Um, so I think I explained last week that I felt like chapters 2 and 3 intro were segmented in a very odd way. So even though all of nomenclature is in chapter 3, I covered that last week in the Zoom session because in my courses, the way I set it up, that's credit quiz 2. It's mostly nomenclature. So I was thinking I'll do that first, kind of put that as one topic, atomic structure, ions, and nomenclature, so that you can be ready to take practice quizzes 2A, 2B, 2C, 2D, and then the credit quiz. Then for this week, my plan was to do the rest of the content, which is mass, moles, molecules, or atoms, percent composition, and empirical and molecular formula. So I have just some questions that I pulled out. I also noticed some language things in the homework that I think could be tricky, even though it's not intended to be. So I just wanted to point that out. But before I start, are there any questions for me? Okay, so far so good. That's good. All right, so these two questions I wanted to pull out because they almost seem like they're the same thing, but they're not. Like number one, it says determine the moles of oxygen atoms in 24.1 moles of CO2. And then the second question says how many bromine atoms are in 35.2 grams of CH2Br2. And these are from the homework, but they're not the problems I assigned. So like I always assign the odds because the answers are in the back, and these are two of the even problems, just somewhere in the chapter 3 homework. And what I wanted to emphasize was in the first question here, we are determining the moles. And in the second question, we are determining the atoms. And I know that maybe at first sort of you're like, what, wait a minute, doesn't it say mole of oxygen atoms? And that's why I feel like it's tricky when it doesn't have to be. But what they're saying is we have the moles of CO2. We want to focus on the oxygen that's present in the CO2. So what we're going to do is basically take the moles of CO2 that were given and go to moles of singular O oxygen atoms. So that probably reminds you a little bit of a mole-to-mole ratio, which from intro chem, we only used if we had a chemical equation. And this is an instance where there's no reaction. We're just looking at carbon dioxide, but we're still going to do the same thing. We're going to look at the fact that in 1 mole of carbon dioxide, there are 2 moles of oxygen because it has a subscript of 2. So I'm going to take the 24.1 moles of CO2, and then for every mole of CO2, I have 2 moles of oxygen atoms. And so I just get twice as much, 48.2 moles of oxygen atoms. So when you see a question like that, determine the moles, right? So specifically, that's what we're looking for is we're just doing mole to mole. We're not using Avogadro's. We're not looking at particles. We're still looking at moles. In the second question, though, it says how many bromine atoms, not moles, but now atoms, are in 35.2 grams of CH2Br2. And so for this one, this I think probably seems like more familiar with what we did in intro chem. We've got a mass, and I'm going to draw a little flow chart of CH2Br2. And what I hope remember from intro chem is the mole is always the first place that you go to. So what we have probably in our memory from intro chem, if not, that's okay. We'll go through it today, is the mole is a substitution for having to count particles. And when we start doing stoichiometry in the next chapter, in a chemical reaction going from A to B, the mole is always the pass through because in a balanced equation, that's what it gives us, or mole-to-mole ratio. But that's coming, right? So when you're doing these calculations, just make sure that the first place you always go is to moles. So we're going to take the mass that was given and take it to moles. Then when we look for particles, we pull in Avogadro's number. And Avogadro's number is 1 mole of a substance is equal to 6.022 times 10 to the 23rd particles. All right, now the particle is a generic term, so it depends on the particle type. We're going to be looking at atoms if we're talking about a singular element, like bromine in this case. But we're going to also have a mole equal to 6.022 times 10 to the 23rd molecules if we're looking at a compound. like the CH2Br2. All right. I don't know why I just did that. This kept happening to me yesterday, so I have to look into it, but I just stopped the video and started back up again. That's usually as technically savvy as I get. Turn it off and start over, and see if that fixes it. Okay. So the conversions to get to particles, and it just froze again, is using Avogadro's number. But the tricky part with Avogadro's, I think, is that the particle type depends on what your substance is. And what we have here is a mass of a compound, which we will first take to the moles of the compound. So because we have a compound, what we're going to do with Avogadro's number is go to molecules first, because that's what we've got. We've got a compound. So we're going to use Avogadro's number to get us to the molecules of CH2Br2. And then from there, we're going to look at atoms using kind of like a mole ratio like we did in the last step. Now, you could technically flip these two. You could do the mole ratio first, do 2 bromine atoms for 1 mole of CH2Br2, just like we did up here, and then use Avogadro's number, right? It doesn't matter if I do A times B or B times A, you're going to get the same answer. So I'll show you what I mean by that. So first thing is, let me start with what we were given, 35.2 grams of CH2Br2. And so last week when we looked at those mass numbers from the periodic table, we were looking at the mass numbers to give us atomic structure, protons, neutrons. But really, if it's a mass, right, it's unit of grams. And if you think about it, this CH2Br2, what I did is I went to the periodic table, added the mass number of 12.01. Hydrogen, I used 1.01, but I took it twice. Bromine is 79.90 taken twice. And I added all that together, and that's where I got this 173.83 grams from. And if you think about it, 174 grams, that's something I can see, right? But I can't see a molecule of bromine. And so it's a substitution we use. It represents 1 mole of CH2Br2. So when we go and find those atomic masses or molar masses from the periodic table, that really gives us the mass of 1 mole of that substance. So what I thought was kind of odd about the way Tro organized the information is that he did atomic mass with elements back in chapter 2, and then did molecular mass and formula mass of compounds and obviously molecules rather than atoms in chapter 3. But I feel like it's the same. So I didn't understand why it was, I don't know. Anyway, that's just me. So we have 173.83. All right. And again, that is the molar mass right from the periodic table, those what we called mass numbers when we were doing atomic structure. There are several names for this. I think I talked about that in the video. Atomic mass if it's an element, molecular mass if it's a covalent compound, formula mass if it's an ionic compound. I like molar mass because it works for everything. It's the mass of a mole. It's really intuitive to me. So whether it's an atom or a molecule or a formula unit, whatever it is, molar mass works. So that's the one I always stick with. So grabbing that right from the periodic table. All right, let me go back. I don't know why it keeps doing that. All right, and so what we did is we took a mass that we were given, divided it by the molar mass to figure out how many moles we have. Basically, we did a ratio. If I know a mole is 174 grams roughly, and I only have 35.2 grams, right, then I know I have less than a mole. And so that first conversion there would help me understand how many moles we have. Now, the next conversion, 1 mole of CH2Br2, according to Avogadro's number, represents 6.022 times 10 to the 23rd. So when you go to use Avogadro's number, what you want to do is just focus really quick. What is the substance, right? The CH2Br2, that's a molecule, right? Not an atom, not something singular. So whatever you have as your mole, that substance, that tells you what the particle type will be. And now in this, we want bromine atoms. So we're going to need one more step. So 1 molecule of the CH2Br2, based on that subscript of 2, has 2 bromine atoms. So what I was saying earlier, boy, it really keeps freezing today. I'm going to have to figure that out. So what I was mentioning earlier is that if you flipped those 2 conversions and you did the mole ratio first, like we did for this example up here, and then did Avogadro's number second, that would have been fine. You could have put 1 mole of CH2Br2 is 2 moles of bromine atoms. 1 mole of bromine atoms is 6.022 times 10 to the 23rd atoms of bromine, right? Or 1 mole of bromine. So you would have had the exact same math, right? It's just whether you want to do the mole ratio first and Avogadro second, or do Avogadro's first and then that ratio second. All right, so I'm going to take on my calculator 35.2, divide by 173.83, multiply by 6.022 EE to the 23, and then multiply that by 2. And to keep 3 sig figs, I get 2.44 times 10 to the 23 bromine atoms. All right, so that hopefully looks really familiar from intro chem, that if we have the mass of the substance, molar mass from the periodic table will take us to moles. Moles will always be the center point. Avogadro's takes us to particles. Just be careful with Avogadro's. Check what your particle type is. If it's a compound, we use molecules. If it was just a singular element like carbon, then we would say atoms, right? So those two questions look at, mass, moles, and molecules. And just really quick, I want to do one other example here, kind of going in reverse. You may have seen these in the homework. All right, so what is the mass of one bromine atom? All right, and so I think there was one of these in the homework. And when you see the 1, you're thinking 1 sig fig, right? But technically it's an exact 1. So the sig figs are limitless, like it's exactly 1.00000, right? So it's not really a measurement, it's an exact value, it's a counted number. And so they would say, well, sig figs are however you want it to be. So if I gave you this question, I would say, give your answer in 4 sig figs or 3 sig figs, whatever it would be. So I have 1 atom of bromine. And so I'm getting rid of atoms on the denominator. So 6.022 times 10 to the 23rd particles, in this case, atoms of bromine, would be equal to 1 mole of bromine. And then in the next conversion, 1 mole of bromine, based on my periodic table, mass number 79.90 grams. So basically, if we take the atomic mass, which is equal to a mole, divide it by Avogadro's number, which is also equal to a mole, we'll get the mass per particle. And you can guess it's going to be a super small number, right? So 1.327 times 10 to the negative 22 grams. And that's just for one singular bromine atom. So with our initial conversions here, I'm going to draw like a little flow chart. Let me rip this page off here really quick. So with our flow charts, which we probably remember from intro chem, right? If we have the mass of a substance, right, we're going to have probably a unit of grams, but of course we could have kilograms or pounds. Your first job, I think, always is go to moles. And the way that you convert mass and moles is using that molar mass, atomic mass, formula mass, molecular mass, whatever you want to call it, from the periodic table. All right, so I'm just going to put PT for periodic table. And then from there, using Avogadro's 6.022 times 10 to the 23rd, we can determine the atoms if we have an element, or we can determine the molecules if we have a compound. And then if we want to take the compound, the molecules of the compound, and break it down one more step to atoms of an element, then what we do for that step is we just we multiply by the subscript for that element in the chemical formula. All right, it froze again, sorry. So let me stop and start back up again. So that last step that I wrote down there with getting from molecules to an individual atom, that's like what we did. Sorry, I have to move this down. That's like what we did up here. We took the mass, right? We used our molar mass from the periodic table to go to moles. Then we used Avogadro's number to get to molecules because we had a compound. All right. And then we looked at that subscript for bromine, which had a subscript of 2. And then that's that last step here, multiplying the subscript to take a molecule and break it down into an individual atom. And so what we knew was for every molecule of CH2Br2, we had 2 bromine atoms. All right, so in terms of the first kind of initial part of like chapter 3 calculations, this is the beginning of it, right? Avogadro's relates moles and particles. Mass and moles is related by the periodic table, the molar mass values, or what we called mass numbers last week. And just one kind of a little step here that may not be as familiar, that if we have the number of molecules and we want to break down to the number of atoms of a specific element in that compound, we just have to look at the subscript for that element in the formula. So that's like the big first part of the calculations. And of course, there's examples in the other videos I posted for the chapter 2 and the chapter 3 notes. So the next thing I want to do is talk about empirical and molecular formulas. And I've got percent composition to do first. So percent composition question I pulled out of the homework, and it says calculate the mass percent composition of nitrogen in HNO3, nitric acid. So we want to figure out the mass percent composition of nitrogen in, sorry, that does not look like an N. All right, in nitric acid, HNO3. So when you see these questions, right, okay, percentages, I got to do some math. I need some numbers. So what I'm looking for is nitrogen in HNO3, right? And times 100, because percentage is always parts per 100. And we're doing it by mass. So we need grams of nitrogen over grams of nitric acid, and then times 100. And since you're not given any measured values, like it doesn't say we took 1 gram of nitrogen and formed 5 grams of nitric acid, right? And then we know it's a 20%. Since we don't have any like mass numbers given to us, what we do is we're going to use those molar mass values from the periodic table. So when I look at hydrogen, mass number of 1.01, remember on the periodic table, it gives you 1.00794. I always round those to 2 decimal places. That's just my preference. I feel like that's good enough. Nitrogen, 14.01. Oxygen has a mass number of 15.9994, but of course that would round to 16.00. And then because it is a O3, I need to take that 16 3 times. So I really have 48 for the total mass of the oxygen, 14.01 for the nitrogen, and 1.01 for the hydrogen. So I have a total of 63.02 grams. So if I want the percentage of nitrogen, I had 14.01 grams of nitrogen in 63.02 grams of the compound. Percentage always means parts per 100, so times 100. And what I get here, again, there's no measurements to use. So how do you really decide sig figs? What I've always done, and I think probably because I saw this the most in my, education, was that molar masses, I always went 2 decimal places. So for my percentages, I always went 2 decimal places. So 22.23%. So that's telling me that nitric acid is 22.23% by mass nitrogen. The rest of it is the hydrogen and the oxygen, but the 22.23% of it is nitrogen. All right. So there were some questions on the homework where it said, okay, now that you know the percent composition, like what would be the mass of sodium in sodium chloride? Something like that. So like, let me give you an example. So what mass of sodium is in 22.7 grams of NaCl, right? So this one, we're taking mass of NaCl to mass of Na. And so what a lot of times they'll kind of suggest doing is to figure out the percent composition of the sodium, just like we did with nitrogen in the last example, and then take that percentage and multiply it by the mass of the compound to get the mass of the sodium. So that's one way you could do it. What I feel like is easier, this is the way I always did it, is okay, I've got 22.7 grams of sodium chloride. What I'm going to say here is when I look at the periodic table, and I add up a sodium, let me write this over here, which is 22.99, and a chlorine, which is 35.45. Again, those are just the mass numbers from the periodic table. Total, that's 58.44 grams of NaCl. So I set up like a little ratio here. Well, since I'm getting rid of grams of NaCl on the bottom, and I know that the molar mass of that is 58.44 grams, what I can do is say, okay, what part of that was the sodium? And that's 22.99 grams. And so what I'm basically doing is the percent composition like I did up here. right? Normally you get your percentage, right, times 100, you get that percentage, and then you have to convert it to decimal form, like 0.2223 for the nitrogen, and then multiply it by the 22.7. It seemed more direct to just do it this way. I know in 58.44 grams of sodium chloride, 22.99 grams of that is sodium. So what would be the mass in the 22.7? So we've canceled out grams of sodium chloride. We've gone to grams of sodium. Again, those are just the mass numbers from the periodic table. So 22.7 times 22.99 divided by 58.44. I'll keep the 3 sig figs. So 8.93 grams of that 22.7 gram of salt would be mass of the sodium. The rest of it would be the chloride. All right. So when you see that, when you're trying to look for the mass of an element that's in this compound mass, you're kind of indirectly doing a percent composition. You're just doing that part of it, right? Instead of getting the percentage, you're doing it as a ratio. And so that, I think that came up in one of the questions. So percent composition, I think most of the time works very smoothly for students. It's just basically setting up, okay, you have this much of this element and this much of the compound. So it's pretty straightforward, but we always have to explain what percent composition is, because when we go to find what's called an empirical or molecular formula, oftentimes we are given a percent composition, and that's what we're supposed to use. So we have to kind of understand what a percent composition means. So first, let me talk about what is an empirical formula and what is a molecular formula. So an empirical formula is the simplest whole number ratio of all the elements in the compound. All right, so simplest whole number ratio. The molecular formula is the true formula. All right, so I often will just refer to that as the true formula. So an example, silver oxalate. Silver is a +1 charge. Oxalate is a -2 charge. So we need 2 silvers to balance the oxalate. When I look at that ionic compound, I've got 2 silvers, 2 carbons, 4 oxygens. I can simplify that ratio. Instead of 2 to 2 to 4, I can go 1 to 1 to 2, right? A lot of times though, empirical and molecular formulas for ionic compounds, they're typically the same. Like sodium chloride, you can't reduce that any further. And that's because typically, right, you always get the least common denominator to cancel out the charges, right? So it's usually the simplest whole number ratio of all the elements in the compound. This is just kind of a special instance. But empirical molecular formula is more commonly used with organic compounds. So if I have butane, which is C4H10, that's the true formula for butane. What I could do is reduce that by a factor of 2. So the empirical there would be C2H5. If I have benzene, C6H6, then I could reduce that by 6 and just have a empirical formula of CH. If I change this and maybe I look at cyclohexane, C6H12, I can still reduce it by 6, but now my empirical formula is CH2. So what I always kind of thought about is the empirical formula, I think of it as a repeating unit. And it will repeat a certain number of times until you make up the true compound. So like that AgCO2 would repeat twice to get to silver oxalate. The butane, the C2H5, would repeat twice to get to the real formula, which is C4H10. The CH, empirical formula for benzene, repeats 6 times until we get to C6H6. And same is true for the CH2 going to cyclohexane. So what I think of is the empirical is this like chunk of the compound, and it repeats a certain number of times until we make up the true molecular formula. So what we're going to do first is kind of go through examples on how to get the empirical formula, and then keep this in mind to help us understand how to get the true molecular formula. So let me push my paper up here really quick. Actually, I'm going to just go to the next page, I think. Let me do this. All right, so there's the empirical formula. Now, what might be a little bit new in this set of homework that we didn't have in intro chem is that I think I had mentioned when you get an empirical formula, a lot of times it's done by GCMS machines. So it would take a hydrocarbon like cyclohexane, and put it into this machine, and it immediately goes through a combustion reaction. And what we may or may not remember from introchem is that in a combustion reaction, all the carbon will come out as CO2 and all the hydrogen will come out as water. And then the machine will do the rest for us. It'll say, okay, well, based on that mass of CO2, then that must have been the mass of carbon in the sample. Based on the mass of the sample that you gave the machine, then that was the percent of carbon in the sample. But now there are going to be some problems where we're going to do that math ourselves. So we'll come back to that in just a second. So first thing is, though, I just want to do more like I think is more of a simple empirical formula, and then we'll look at one of those combustion analysis. All right, so let's say I've got an empirical formula. Yeah, I'm in the, okay. And it says I have 2.128 grams of beryllium, 7.557 grams of sulfur, and 15.107 grams of oxygen. So typically when you go to do an empirical formula, that's what you need to start with. You need to start with the mass of each element. Now, when you look at a formula, all right, let me go back to this page really quick, like C4H10, that 4 and 10, those are not mass ratios, right? This is not telling me 4 grams of carbon for 10 grams of hydrogen. It's telling me moles, right? For every 4 moles of carbon, there's 10 moles of hydrogen. So what we need to do is take those mass values and determine how many moles that would be for each of those elements. And like we were talking about earlier, what that means is we're going to divide by the molar mass for each of those elements. And the molar mass comes right from the periodic table. Beryllium, not one I use as much, but molar mass 9.012. Sulfur, depends on the table you look at sometimes, 32.07. And oxygen, 16.00. All right. So at this point, just a little note, a lot of times students want to start rounding, but don't round just yet. We need to keep our sig figs here. So 2.128 for the beryllium divided by 9.012, I get 0.2361 moles of beryllium. For the sulfur, 7.557 divided by 32.07, I get 0.2356 moles. And then for the oxygen, 15.107 divided by 16.00, I get 0.9442. All right, and that would be my moles of each of those elements. And basically at this point, I have the formula, right? I could write it as Be 0.2361, sulfur 0.2356, and oxygen 0.9442, right? But we don't ever write formulas that way. We prefer nice, pretty whole numbers, right? So what we're going to do is we're going to simplify this. And what we do is we divide by the smallest number of moles present, and we're just reducing the formula. And hopefully we're going to get a nice whole number ratio, but it doesn't always work. So I look at my numbers of moles. It looks like sulfur is just slightly less than the beryllium. So since that's my smallest, I'm going to divide everything through by that 0.2356. And you got to do everything. And the reason for that is once you determine your number of moles, like we did up in this step right up above, we just finished that, that is the mole ratio. So anything I do to one, I have to do to the other to keep it fixed. So I need to multiply everything through by 0.2356. All right, so the sulfur will obviously go to 1. So let me take the 0.2361 divided by 0.2356. I get 1.002. And for the oxygen, 0.9442 divided by 0.2356, I get 4.008. All right. Now, this next step here, I'm going to put a question mark. All right. Sometimes you need what's called a multiplier. If you don't get whole numbers in this step, then you might have to do a multiplier. And here are the scenarios that I want you to sort of be prepared for. All right, so this is an if, because for us, we had everything as nice whole numbers, so we didn't have to worry about this. But if we had something that ended in a 0.5, right, that's a half, my multiplier would be a 2. If something ended in a 0.25, that's a quarter, so I'd multiply by a 4. And if something had ended in a 0.33, that's a third, so your multiplier would be a 3. Now, occasionally, doesn't happen often, but sometimes you'll get a problem where like one of the numbers ends in a 0.5 and the other one ends in a 0.25. Then take the least common multiple of those two multipliers. So a 4 would work for the quarter and the 5, right? The half. If you had a number that ended in a 0.5 and another one in a 0.33, then you'd have to do a multiplier of a 6 to get both of them to a whole number. So it doesn't happen often, but occasionally it does. Now, in this case, like I said, we don't have that issue. We had a nice 1:1:4 ratio. So we know that our empirical formula is BeSO4, right? Beryllium sulfate looks like the empirical formula. All right. And just one thing I want to note, if you do have to use a multiplier, make sure you do it to all of the elements, not just the ones that have the decimal, but do it to everything in that compound. So in this compound, we have 1 beryllium for 1 sulfur for 4 oxygens. All right. So let's try another one. All right. Let's say instead of given mass measurements, let's say we were given percent composition. Right. So we fed it through the GCMS and the GCMS gives us a percent composition. And we've got a compound that is 58.80% carbon. And then we have 9.87% hydrogen. And then the last element, the oxygen, is 31.33%. So if you're given a percent composition, just assume that you have 100 grams of the compound, because then this is nice and easy. That means we have 58.80 grams of carbon, 9.87 grams of hydrogen, and 31.33 grams of oxygen. And it's okay to make that assumption because that mass relationship would be the same, the ratio, whether you had 100 grams or 1,000 grams or 2,000 grams, it doesn't matter. So just change your percent sign to grams, essentially, and that'll get you your mass of each element. All right, so that is step 1, right? We always start with mass of each element. Then we go to moles. So we're going to grab the molar masses from the periodic table. So for carbon, we're going to divide by 12.01. For hydrogen, 1.01. And then for oxygen, 16.00. All right, keeping my sig figs. For my moles of carbon, I get 4.896. For my moles of hydrogen with only 3 sig figs, because that was the percentage, I have 9.77. And then for the oxygen, I get 1.958. All right, so we got our moles of each. So that is our mole ratio, just not pretty subscripts. So at this step, we divide through by the smallest and make sure we do everything there. So not just the compound that has the smallest number of moles, but all of them. Because again, we want to keep that ratio nice and fixed. So the oxygen has the lowest amount. So I'm going to divide by 1.958. Oxygen's going to go to 1. All right. And I'm going to do the same thing for the carbon and the hydrogen. So for carbon, 4.896 divided by 1.958, I get 2.501. And then for the hydrogen, 9.77 divided by 1.958, I get 4.99. Okay, so the 1 obviously stays a 1. That's a nice whole number. The 4.99, it just froze again, will round to a 5. That's close enough, right? That's definitely close enough. But then on this one, the 2.5, we don't want to round that to 3. So that's one of those situations I gave you earlier. We have a 2.5, which predicts a multiplier of 2. Makes sense. It's a half, right? So we're going to take that, and the 2.5 means we're needing to multiply by 2. Now, the multiplier, make sure you do it to every element there, not just the 2.5, but again, you're trying to keep that ratio fixed. So if I have a 2.5 to 5 to 1, then I need to change that to times 2 times 2. The oxygen becomes a 2, the hydrogen becomes a 10, and the carbon becomes a 5. And so now what I have is C5H10O2. All right, so that would be the empirical formula for whatever that compound was. All right, again, not necessarily the true compound, but that is the empirical. It gives us the simplest whole number ratio of all the elements in the compound. All right, Now, the percent composition from a combustion analysis, that was the one that we really didn't do in intro chem. So that's the one I wanted to make sure and show you how to do. So this one has a little bit more work to it. All right, so I'm just trying to move that up. So next question here. It says we've got a combustion analysis of naphthalene, which is a hydrocarbon. And this hydrocarbon, which only contains carbon and hydrogen, when it goes through that combustion reaction, it says that it produces 8.80 grams of carbon dioxide. And it says that it produces 1.44 grams of water. So what's important to kind of conceptualize here is that in that 8.80 grams of carbon dioxide, the carbon came from the hydrocarbon. In the 1.44 grams of water, the hydrogen came from this hydrocarbon. Now the oxygen comes from oxygen in the air because it's a combustion reaction. All right, so what I'm going to do here is I'm going to take my 8.80 grams of carbon dioxide, and I'm going to do like we did earlier with the sodium, right? The molar mass of carbon dioxide from the periodic table, 44.01 grams. And then the mass of just the carbon is 12.01. So basically, again, doing a percent composition. So figuring out the percent composition of carbon in the CO2 to then figure out the mass of carbon that's in that sample of CO2. And in that 8.80 grams, 2.40 grams of it is carbon. Same thing, but now with the hydrogen, I had 1.44 grams of water. Periodic table tells me that the molar mass of water is 18.02 grams. Now in that, be careful, there's two hydrogens here. So 2.02 for the two hydrogens. All right, and that's okay. We're still looking at how much mass of hydrogen was here. So 1.44 times 2.02 divided by 18.02. Calculation tells me that in that 1.44 grams, only 0.161 grams of it was the hydrogen. All right. So basically, again, figuring out the percent composition of carbon in CO2, and then figuring out the mass of carbon in that 8.80 gram sample. We just want the carbon because remember with an empirical formula, that's what you have to start with. You have to start with the mass of each element. So I know in this C6Hy hydrocarbon, I know 2.40 grams is carbon and 0.161 grams is hydrogen. And so from that, I want to figure out, okay, well, what is the formula? What's the empirical formula then? Now, I think there's maybe a question on the homework where it's a hydrocarbon that contains oxygen also. And it just kind of a heads up if that happens. Like if it tells me that I used 5 grams of hydrocarbon and I know it produced the CO2 and the water, but it tells me that there's also oxygen in this compound. Then I follow, okay, if there's 5 grams total for the hydrocarbon and 2.4 grams is carbon, 0.16 gram is hydrogen, then the difference of those two from the 5 grams of the compound would tell me the mass of the oxygen that must be there too. But in this example, there was only carbon, only hydrogen. So I already got that from my CO2 and H2O. So I'm done. But that was the mass of my compound that was in the machine. All right. So in that compound, the sample, right, 2.40 grams was carbon, 0.161 grams was hydrogen. And so now I can do an empirical formula. So I've got 2.40 grams of carbon, 0.161 grams of hydrogen. We go to moles first. So we're going to divide by that atomic mass or molar mass, whatever you want to call it from the periodic table. So for hydrogen, I have 0.160 moles. For the carbon, what keeps freezing today? Maybe because it's freezing outside. So for the carbon, the 2.4 divided by 12.01, I get 0.1, no, with 3 sig figs, change that. I get 0.200. I have to round it up. All right. So just typing it in really quick one more time, making sure I didn't type something in wrong. So yeah, 0.200 moles of carbon. And then for the hydrogen, 0.160. Actually, that one actually came out 0.159. So I may have typed it in. Oh, I know why, because I had all the digits left in the calculator. All right. So 0.159. Now we divide by the smallest, which is going to be the hydrogen. So hydrogen will go to 1. For the carbon, 0.2 divided by 0.159 gives me 1.26. Okay, so that was another multiplier. The 0.26, right, that's closest to a 0.25. So that means a multiplier of 4. But of course, we do everything, right? So 1.26 times 4 gets me to a 5. And then the 1 times 4 gets me to a 4. So this compound is C5H4. That would be my, again, empirical formula for whatever this compound is. All right, so that's how you can use a combustion analysis. Like I said, when we use the GCMS, it does all of that work for us, which is super nice. And it just gives us the percent composition, but we can do it. We know how to do it. It's just getting basically a percent composition of the carbon dioxide in the water to figure out mass of carbon and mass of hydrogen. So that's empirical formula. The last part of the chapter is, okay, what about a molecular formula? So with a molecular formula, what we talked about was the empirical formula is a repeating unit. So this C5H4 would have to repeat a certain number of times until you make up the true compound. Now, the only way to know that is you would have to be given the molar mass of the molecular formula. It has to be given because you don't know what the molecular formula is. So when you're thinking about like that repeating factor, which I'll just call X, right? So like CH for the benzene times X gets us to C6H6. To figure out what that repeating factor is, you want to take the molar mass of the true molecular formula. How much does the whole true compound weigh according to the periodic table? Then divide it by the molar mass of that repeating unit, the empirical formula. And it kind of makes sense. Like if I look at this, benzene has a molar mass of 78 roughly, and CH is 13, and 13 goes into 78 6 times. So that's how we're going to figure this out. We're just going to use the molar mass. Now the molar mass of the true compound would have to be given. So you'll notice that in the questions. So an example here, just going kind of in that last step, I think we're on number 8. It says we've got a compound with an empirical formula of C3H2N. So that's the empirical, simplest whole number ratio. And then what we're also told is that the molecular formula has a molar mass of 312.29 grams. So really, again, all we know about the molecular formula is that it is the C3H2N, whoops, sorry about that, repeated X number of times, and it has a total molar mass of 312.29 grams. So that's what we understand about the empirical and molecular formula. The true molecular formula molar mass has to be given because we don't know what it is, right? The empirical formula we were told. So that repeating unit repeats X number of times until we get to this complete molar mass of 312.29. So always what you do first here is we're going to get the molar mass of that empirical repeating piece. So when I look at this, carbon is 12.01, but I need to take that 3 times because the empirical formula, the carbon has a subscript of 3. Hydrogen is 1.01, but I have to take that twice since it says H2. And then the nitrogen molar mass from the periodic table is 14.01. So 14.01 plus 2.02 plus 36.03, I get 52.06 for the mass of that repeating piece. So then the last part of this is, okay, well, how many times does 52 repeat until I get to 312? So to figure out what X is, we're going to take the molar mass of the true compound, again, given, and I'll just mark that as the true, divided by the molar mass of our empirical that we got from the periodic table, 52.06. And this right here, we don't need multipliers for this, right? This should always be a whole number. So I'm going to take my 312.29 divided by 52.06, and I get a factor of 6. So what I now know is that empirical unit repeated 6 times until I get to the true compound of 312.29 molar mass. So my true molecular formula, I'm going to take my empirical formula and multiply all the subscripts through by 6. So C3 becomes 18, H2 becomes 12, and then N1 becomes 6. So I just took that factor, the repeating factor, and multiply all the subscripts through by that number. So C18, H12, N6. So that's how we get to a true molecular formula from an empirical formula. All right, in terms of the calculations then for chapter 3 and for credit quiz 3, you have everything you need at this point. It's a big focus on, I think, a review from Introchem, the mass, moles, molecules, particles, that kind of thing. And then an empirical formula, percent composition, and then how to get that true molecular formula at the end. So hopefully this Zoom session sort of kind of summed everything up. Next week, we've got chapter 4, and there we're going to be doing some equation writing and some stoichiometry. So again, it's going to feel very familiar. I think usually like the first half of Chem 1 hopefully feels pretty comfortable. Like we learned the combustion analysis today. That was something a little bit new, but we're kind of building slowly on what we hopefully remember from intro Chem. But I think as far as today goes, I think that's everything that I had planned, but I can certainly take whatever questions if you all have any. And if you don't have any, then, I wish you a great day and we'll meet back next week. But does anybody have any questions for me? And you can feel free to type them in the chat if you prefer.
No, I don't have no questions, Miss. Thank you.
Thank you, Ramon. And there are videos for the chapter 3 notes. So I really debated on how to present chapter 2 and chapter 3 and how to quiz because the content is sort of different. So what I did is you'll see, you probably have already seen this, but in the chapter 2 and chapter 3 folder, I present the chapter 2 notes, and then I have the videos that go with the chapter 2 notes. And then I have the chapter 3 notes and the videos that go with the chapter 3 notes. So it's me working through those notes. Then what I did is I kind of separated it. So the nomenclature, atomic structure that I put on credit quiz 2, that's what's covered on practice quiz 2A, 2B, 2C, 2D. Then the content we went through today, this is all what you need for practice quiz 3A, 3B, 3C, and then for credit quiz 3. So hopefully it makes sense the way that I did it. I wasn't trying to be confusing, I promise. Next week, it'll be more streamlined because it's just chapter 4 in the folder. So that's what we'll be going through next week. But hopefully that makes sense. If you have any questions for me, let me know. But just a big heads up, and I probably should write this down, that if you haven't already, credit quiz 2 is due February 1st. And credit quiz 3. So both of them are due February 1st at 11:59 p.m. All right, so it's always Tuesday, right? That's when I have all the quizzes due for this class. So nothing is due tonight, but both of those credit quizzes are due a week from today at 11:59 p.m. So if you have any questions for me, definitely please let me know. We can always arrange for another Zoom session. There's also, like I said, the other videos posted in there. And then I did do another one of those combustion analysis questions. I had the one on the homework that I thought, oh, we haven't done this in intro, so let me do that. So you'll notice that video is posted too of me working out one more of those combustion analysis questions. But if there's anything else you need from me, please let me know. But if not, I wish you a great week.
Have a nice day, Miss.
You too. Thank you.
Thank you, Professor Emerson.
Thank you. Have a great day.